All right. So today we'll talk about feedback control. If you are looking at that book that I recommended at the beginning of the semester, Oppenheimer and Wilsky, that's chapter 11. So think of this as an application of all the transfer function concepts we've been discussing, because a lot of the times the way you design feedback controllers is by using ideas from transfer functions, poles, zeros, and all that stuff. So in this feedback loop, R of t is a reference signal that you want to track. All right? It can be a simple set point, the velocity that you like your car to go with, or it can be a signal that you want to track, maybe something like a sinusoidal, maybe a robot arm is trying to pick up something from somewhere, bringing it there. So it can be a time-varying reference as well. And y of t is the physical variable you're interested in having follow r of t, so the speed of your car if you're doing cruise control. So there are two blocks here. HP of s is the system you're actually trying to control. It's a dynamical system. It has some things that you can manipulate in it. Maybe the throttle opening for a cruise control problem, or the motor voltage you apply to a DC motor to control the position of a robot arm, right? Things that you can actually manipulate. So from x to y, so y is the physical variable of interest to you, so you have this transfer function describing it, okay? Usually that part that I highlighted, it's called the plant. I mentioned this last time. I think it's a reference to, chemical plants, where you have a lot of chemical processes you're trying to control. And usually that model that is now represented with a transfer function is typically based on some physical principles, right? And now what you're doing in this feedback loop is you look at the output, you compare it to the reference you want to follow, and you generate this error signal, E, okay? And then you look at E to determine what input you apply to the plant. So that's the fundamental paradigm of control. You look at the error and take some control action accordingly. What do you do based on E? There are several things you can do. The more complex schemes will involve a controller that itself is a transfer function. That means it has its own dynamical variables and so on. In the simplest case, you can take a constant gain feedback. Perhaps constant gain k, in which case you don't need a transfer function. It's just the transfer function is k, right? All right? So then the goal, again, is for y to track r. So in addition, of course, to tracking r, fundamentally the first constraint is that the feedback loop should have no instability. So when you evaluate the transfer function from r to y in closed loop, that transfer function needs to have poles in the left half plane, because that's our stability criterion, right? You don't want to generate instability with your controller. It's often the opposite. Your plant may actually have instabilities, and you may be trying to stabilize the plant with your control action, not the opposite. Okay? So we looked at transfer functions in feedback loops last time, or maybe the lecture before. So if I look at the transfer function from the reference to the output, which of course is the ratio of the Laplace transform of the output to the Laplace transform of the reference, let's see how many of you remember. What goes in the numerator? Hint, when there is a negative sign here, you get 1 plus something. And if this was positive, it would have been negative. But anyway, so this is negative feedback. What goes in the numerator is the product of everything you see in the loop, right? In this case, it's, what you see in the feed-forward path. So in this case, it's HC of S times HP of S, right? And then what goes in the denominator is 1 plus the product of everything you see in the loop. In this case, everything you see in the loop is what you see in the feed-forward. It's still HC of S times HP of S. All right? So if you're doing constant gain control, So if your control action is simply looking at the error, multiplying it by a constant, and making it the input to the plant, then this just becomes k times HP of s by 1 plus k times HP of s, right? So HP of s had its own poles and zeros, right? Now that we close the closed loop system has a new set of poles that are dictated by your choice of k. How do I find the poles of the closed loop system? I mean, normally HP will have a numerator, denominator, so you'll simplify this expression. So if HP is like n of s by d of s, numerator by denominator, then you can simplify this as k n by d, right? 1 plus k n by d, multiply everything by d, you get kn d plus kn, right? So therefore the poles will be determined by this new polynomial you have in the denominator, right? Yes? So we can simply, without having to split this into numerator, denominator, etc., we can just say that the closed loop poles will satisfy 1 plus k times HP of s equal to 0, right? Because then what you get in the denominator here is 0, so it blows up, right? So that's what happens at the poles, the definition of a pole, singularities, right? Okay, so that means that with our choice of k, we were able to move the poles of HP of s with the feedback loop, right? And that's one of the fundamental questions in designing controllers. How should we select the gain k so that the overall transfer function has desirable properties, in particular stability, which implies all the poles should be in the left half plane. But more than stability, you may want to worry about where you put those poles, because they'll determine the closed loop behavior, how well you track a reference signal. Okay? So let's look at some examples to make this more concrete. So we'll start with a simple example where we have a mass. This could be a car. Actually, the longitudinal motion models for vehicles is not much more complicated what I'm going to write now. It's very simple. So X is the force you apply. And let's say what we are trying to control is the speed. So Y is going to be the speed. All right. So what is a first principles model that relates Y to force? So m times the acceleration, which would be dy dt, right? Because y is speed, the derivative of that is acceleration, should be equal to force, right? So if you want to be a little fancy, you may want to add some drag terms that depend on velocity, etc. We're not going to go there. We'll keep it simple. So you're moving on a frictionless surface. There's nothing to resist motion, right? All right. So so this is our plant. Remember, plant relates x to y, right? X is what I can manipulate. That's the force I apply. That's my control variable. And y, speed, is what I'm trying to regulate. So what is the transfer function of this plant? So that I'm going to call plant because it relates x to y. So what is HP of s? That is y of s by x of s. How do we get transfer functions from differential equations like this? Take Laplace transforms of both sides. The left-hand side is ms times y, right? The right-hand side is x, so you'll get 1 over ms. Any zeros? No. Any poles? Pole at s equals 0. But note, this is an open loop pole. If I don't do anything, my plant has a pole at s equal to 0. When I close the loop, that pole is going to change. All right, so what is the closed loop transfer function? Let's just write it out. So closed loop transfer function, remember, is k times hp of s by okay. Plus k hp of s. So hp of s was very simple. It was 1 over ms, right? So you have k over m s plus 1 over k over m s. Oh yeah, there's no s. You're right. Yeah, k over m, right? No, m is everything is in the denominator. You're right. Okay. And then multiply things by s, so you'll get k over m, s plus k over m. So you have a closed loop pole at where? Negative k over m. And there you go. So you had a pole at 0, you close the feedback loop, you moved it to the left half plane, right? So if I make a sketch of the complex plane, real and imaginary axis, we usually represent poles with a cross. So I'm going to use a cross, or what do you call it? Yeah, I guess cross is fine. At 0 for the open loop pole. And as I increase k, what happens to that pole? Where does it move? It remains real, right? There's no complex value here. K is going to increase from 0. I'm tuning a feedback gain, right? K is 0, my pole is here, because k is 0 means no feedback, right? If I increase k, in which direction would that pole move? To the left, right? If I increase k further, then you get an even more negative number for your pole, right? So that means, as I increase k, think of turning a knob where you are choosing the gain k. Your closed loop pole is moving from 0 to negative infinity, right? So this goes to negative infinity as k goes to infinity, right? So the pole moves on the real line. With feedback, we can move it as we wish, right? Now, what's the effect of moving it? Let's say we're trying to, since this looks like a cruise control problem, right? We're regulating the speed. So if I apply a step input, if r of t is a step, I would want to know how my output would respond to that, right? So the first question is, am I going to, if I have a step jump of 1, is my output also going to converge to 1? How do I judge that? I guess we call this h of s, right, for the closed loop. Let me put CL for closed loop, CL of s, right? Yeah, so the DC gain, right? HCl 0 is the DC gain, and that tells you how much a constant input would be multiplied at the output, right? So that's what DC gain does. And if I substitute s equal to 0, I get the numerator and denominator equal to each other, so I get 1. So clearly, I expect a rise, and in steady state, I expect to settle at 1, right? The question, though, is how do I go to 1? How fast? Depends on k, yes. Looking at this, can you tell me the... if I gave you this closed loop transfer function, if I told you I want to know the output y of s when r of s is an input, right? What do? I just multiply the transfer function k over m by s plus k over m with what? 1 over s, which is the Laplace transform of the unit step, right? 1 over s. So how do I back out from this y of t? That requires an inverse Laplace transform. In this course, we don't do, very complex analysis types of things, contour integrals. We just do partial fraction expansions. Those always work when you have rational transfer functions like this, polynomial by polynomial, right? So you want to find you want to write it in this form, A over S plus B over S plus K over M. Make sense? And now you want to find A and B. So I'm basically doing a quick review of partial fraction expansions. You'll get in the numerator A plus B S, is that right? Plus A K by M, S times S plus K by M. All right, so how can I make the numerator match this? A plus B should be 0, and A times K over M should match K over M. Therefore, A should be equal to 1, and from this, B should be negative 1, right? So therefore, we found our y of s. It's simply 1 over s minus 1 over s. Is that right? Did I do this right? As plus bs, ak over m. Okay. So that's correct? K over m. Is it? Tell me it is. Okay. All right. So then y of t is what? U of t, that came from 1 over s. And then this is what? E to the negative k over m times t u of t. Essentially 1 minus e to the negative k over m t times u of t. So what's going on here? At time equal to 0, I have 1 minus 1. So I start at 0, right? I start at 0, and then what happens? Exponentially, I converge to 1. It's going to look like this. That's your y of t. That's your reference. Should I worry about instabilities? No, the closed loop pole is in the left half plane. That's taken care of, right? And y follows r as I wanted to have, right? Question is, how fast can I make this go faster? Yeah, if I make k here bigger, that exponential dies out faster and I get to 1 faster, right? So increasing k has this effect. So as I increase k, you're going to converge to 1 faster and faster. So in this particular example, where the model is very simple, just cranking up the gain will give us good performance. We get stability, and we follow step inputs perfectly and quite fast. All right? So that's an example of feedback control. But this idea of, turn the knob, increase the gain, and life gets better, that's not often true. There are side effects that you suffer by increasing k, which are not evident in this particular example because the model is so simple. It's just the 1 over s, right? Okay, so any questions here? All right, let's switch to another example. Again, the same system. Again, that car, M. Only the shape is a little deformed now. That wasn't intentional. Again, X is force. But now let's say I'm trying to make the car go somewhere and sit there, and even when I push it from there, it comes back. So I want to basically stabilize the vehicle at a certain point. That's more appropriate perhaps for a robot, or another application is, ships don't really moor these days. I don't know if you knew that. There's GPS, right? So they have these thrusters on the sides, so they know where they want to be. They don't have these iron things. Some may, but most of the time they don't. So there's a feedback controller that keeps it in place. It learns from the GPS if it's drifted and applies action to come back to where it wants to be, right? So this is an example along those lines, right? You're trying to control the position, right? So y is now position, not velocity. We reserve the name y for the variable that we are trying to regulate. Okay? For the same system, y can take on different meanings depending on the application. For cruise control, it would be velocity. For position control, it would be position. So now the model becomes a little different. I have to differentiate y position twice to get an acceleration, right? Yes? Okay, d squared y dt squared is now x. All right? What that means is if I want to write a transfer function, I'll have s squared because I differentiated twice. Every differentiation is multiplication with s, right? So I multiply twice. M s squared y of s is x of s. Therefore, our plant transfer function is 1 over m s squared. All right? Yes? Now we apply feedback. What does feedback do? It does what's in this block diagram here. R is a reference. You tell the car to go there and stay there, right? Perhaps, again, let's think about a step reference. So you're telling the car to go here and sit there and wait, right? And so the controller looks at where you are, compares it to where you want to be. That's the error signal. Now it's going to multiply it by a constant and apply it as a force. When it reaches the right spot, the error becomes 0, so you apply no force. That makes sense, right? So then you don't move around. So let's go back to this. So the closed-loop transfer function is, again, k times the open-loop transfer function. But now it's 1 over s squared plus 1 k over m s squared. Okay, that's what's going on. So, all right. In the notes, I added a little damping, all right? So, yeah, let's add a little damping here. So, to the left-hand side, I'm going to add a certain amount of damping, dy dt. I could add friction too, but that's more like, proportional to the speed. Air drag type of thing. Okay? X, all right? So what does that really change? So I'm going to get bs here, b times s, bs. Okay, that's the only difference, all right? But that all has to change now. So k s ms plus b. So I'm basically rewriting this in this form, s times ms plus b. So you can immediately tell me where the open loop poles are. One is at s equal to 0. The other is at s equals negative b over m. Yes? Okay. So what happens in closed loop? Let's write the closed loop transfer function. It's that by 1 plus the same expression. All right? And if I simplify that, I get k by m s squared plus bs plus k. Okay? What's my DC gain? H of 0. Did I do something wrong? What? It's the usual formula where you write k times the transfer function, which is 1 over s ms plus b, divided. It's this formula. This one. Huh? Which doesn't mean I wrote this correctly, but I think I did for a change. It is. Okay, good. So what is h of 0? The DC gain is 1. So if I apply a step force with this controller, with a constant k controller, the output will go to that steady state, right? So we are able to follow the references, at least in steady state. The next question we ask is, how do we get to the steady state, right? Comfortably, slowly, fast? Do we do overshoots? And we'll figure that out from what? The closed loop poles. They tell us everything, right? So what are the closed loop poles? They are the roots of this, right? And you probably sometime in your life you've seen a formula for the roots of a second order polynomial. Yes. Okay. So they are, and you probably saw that more recently than I did, so help me out. 2m, okay. Plus minus square root 4km. Is that right? Okay. So now, what happens when k is equal to 0 in this formula? Forget it, you're jumping too many steps there. If I put k equal to 0, there's no square root of anything, right? So I get negative b by 2m. Wait, what is going on here? What? I should be getting the same things here. Oh, s equal to 0 and s equal, if not, I wrote something wrong. Oh, yeah, of course. Negative b plus minus b, right? So either I get negative 2b by 2m, which is negative b over m, which is this guy, or when it's positive, negative b plus b, it's 0, so I get this one, okay? As expected. Okay, good. So it's always good to check that at k equal to 0, you recover the open loop poles, right? And then now let's make a sketch. You gotta get used to these sketches of how the poles move in the complex plane as you change a gain. So open loop, the pole, one pole is at s equal to 0, the other pole is at negative b over m. Now let's turn the knob just a little slightly to a slightly positive value of k. How did those guys move? Clearly, the square root term will still be square root of a positive term, right? So you'll start with negative b over 2m plus minus something very close to b, right? So on one end, you'll come close to here, to 0. The other end, you'll come close to here. If I move k just a little bit, right? If I move k more, in what direction do those move? Further in, right? And what happens? They keep moving closer, right? And note the center is negative b over 2m, which is what you're seeing here, right? So as I increase k, I get, what the square root term becomes closer and closer to 0, so I'm coming closer and closer to the middle. So they are moving towards the middle, towards each other, both poles, right? And then comes a point when b squared minus 4km is 0. And at that point, k is equal to b squared by 4m, right? At that value of the gain, I have two repeated poles, both in the center. So the two poles started moving towards each other. They clashed in the middle, right? All right, now we have repeated poles. What happens if I increase k beyond this value here? Now, what I have here is negative. So that will introduce plus minus j times something, right? And the real part from that point on is stuck here at negative b over 2m, right? So going a little above this value of k, oh, no, that's not what I meant. Okay. I'm going to have poles here and here, right? Or if I increase k, they will go up. And of course, there's the conjugate of that, right? So the poles met in the middle, and then they break away. One goes up, the other goes down. So they move on this line. And if I increase k to infinity, they will go to infinity. The real part will stay the same, but the imaginary part will become larger and larger, right? So what do you make of, what is the response of a second order system when you have complex conjugate poles? That means oscillations. But remember, we still have h of 0 equal to 1, that means we will get to 1 eventually. And the poles are, after all, in the left half plane, so there's no instability. We will go to 1. But the question is, how do we get there? So if k is large, then going there will not be fun. You're going to have, so this is the time axis now. This is the reference. R of t is a step. And this is the actual y. If I increase the gain too much, then y is going to look a little crazy. Right? There will be a lot of oscillations because of those complex conjugate poles. Right? It will settle, and the envelope is actually determined by the real part, which is b over 2m. So, depending on how much damping you have here, you are going to converge to 1. But you may do a lot of oscillations, a huge overshoot before. And it's not clear if you want that or not. Right? Again, if you're trying to moor a ship, you don't want these overshoots that might make you hit some obstacle somewhere. If B is what? B is very large, then but still, depending on the K, you can have big overshoots which you may not want. Okay. So that's when K is bigger than that critical value, which was B squared over 4m. Okay. What would happen if I chose K right here, just so that it gave me two closed loop poles exactly in the middle? Then I would go smoothly, right? So in that case, the output would be far smoother. Roughly, the convergence rate would be similar because it's still determined by the real part, which is the same. But it would be smoother and no overshoots. Right? So it's going to look like that. Okay? If I choose K smaller, then what happens? Now there are two poles, right? And they are not the same. So one will be close to 0, one will be close to negative. So we're talking about this situation. One is here, right? One is here. So you can do your usual partial fraction expansion. You'll get, the output will be the sum of two terms, right? One will be a pole associated with this, so that converges very slowly. And the other one will be associated with this. It will be much faster. So the behavior will be dominated by the slower convergence. So you would get some behavior where convergence takes longer, like this. So this all points to the importance of selecting that gain and how selecting the gain actually shapes the response of the system to a reference signal. And keep in mind that the type of control we're talking about here is the simplest. We have one single gain that we multiply with the error before applying it to the plant, and that's that. So we're just discussing how to choose that. Normally, you may have more complicated controllers that do a lot more than that, and we'll talk about some of those later on. Okay? So these two examples made one question very explicit. The question is, if I close the feedback with a constant gain K, how do the closed loop poles move? Therefore, how should I select my gain K to get a desired response from the system? So this is actually, there's a set of tools called root locus analysis, which is actually, without calling it so, is what we did in these examples. This plot here, the orange plot, is a root locus for this plant, where the transfer function is this. Okay? Root locus tells you how the roots, the poles, move as you change K. What is their trace? Imagine turning K, and imagine that as the poles move, they mark where they passed. They turn it orange in our picture, right? So at the end of the day, as K goes from 0 to infinity, what were the points traced by those poles on their way, right? So that is the root locus. So that gives you like a menu of closed loop pole locations that you could put your poles at by selecting an appropriate gain. All right? If I want my closed loop poles here and here, there's a gain that does that, right? If I want my closed loop poles here and here, there's another gain that does that, right? So, but if I want closed loop poles here and here, with this architecture of a constant gain controller, there's no way to get there. Okay, you would have to do other controllers. Okay, so think of the root locus as a menu to choose from. These are the locations where, with a constant gain controller, you can put your closed loop poles at. Okay, so this was an even simpler. Where is this? Yeah, here. This here was an even simpler root locus. We had a single open loop pole, and it moved to the left. That's also a root locus for a simpler system. So what does the root locus look like for more complicated transfer functions? There are a set of rules. I'll just point to the highlights of this, because in the old days this was a, the analysis tool was important before computers and stuff, because by hand people could make a sketch of how the poles are going to move and try to estimate how they should select K. Nowadays you can do this on MATLAB, Python, whatever you're using. But still there's a lot of intuition to be gained from a few basic principles about the root locus, what it looks like. Okay? So in general, the idea is the root locus tells us how do the roots of 1 plus k h of s equal to 0 move as k goes from 0 to infinity. Okay, root locus answers that question. There are a number of rules for sketching root loci. We're only going to highlight a few of them that are important for building intuition, nothing more. But the basic principle on which these rules are based is very simple. If a point, so this is the basic principle, if a point in the complex plane, if S sub 0, let's say, S naught, is on the root locus, that means there exists a k, call it k0, positive, such that 1 plus k0 h of s0 is equal to 0, right? So if that's the case, what is h of s0? Let's say positive, strictly positive. What is h of s0? Minus 1 over k naught. And k naught is positive, so this is a negative number, right? Negative and real number. Okay? So that gives us a very simple principle to determine if a given point on the complex plane is on the root locus or not. Is h of that number a negative real number or not? Okay? So what's the signature of a negative complex number? If I look at the phase of that number, what is it? 180 degrees, pi or minus pi, they're all the same, right? Okay, so essentially root locus is really a sketch of the points in the complex plane for which h of s has a phase of 180 degrees. Okay? Every rule that you ever see about root locus is derived from this very simple principle. Okay? So all the words here collapse to one basic principle. Look for points in the complex plane for which points S, for which h of s has phase equal to 180 degrees. That's it. All right, so what are some of these rules for sketching the root locus? So the way we start is we usually make a plot of the open loop poles and zeros. Okay? So you write your transfer function h of s, the open loop transfer function, in this form. Zeros, beta 1 to beta m, and then poles, call them alpha 1 to alpha n. Okay? So we have zeros at beta, poles at alpha. Okay? So as k goes to 0, what are the roots of 1 plus k h of s equal to 0? Note that this simply means h of s is negative 1 over k, right? So if k is going to 0, where is negative 1 over k going? Infinity, right? So then we're looking for points s for which h of s really is blowing up. And those are the poles, right? So that means this is, or converging to infinity, therefore s is going to the poles, right? So that means for k equal to 0, root locus is at the open loop poles. And that's what we observed anyway, right? In both of our examples, for k equal to 0, we started at the open loop poles, and then we started turning k, and things started moving from there, right? So that's the first principle. K equal to 0 should recover the open loop poles. Now, what happens as k goes to infinity? Now I'm asking for solutions to h of s equals 0, right? And when does that happen? When h of s has a 0 at that point, right? So that means as k goes to infinity, root locus, or how many zeros do we have? We have m, right? And we'll make an assumption that we don't have more zeros than poles, so m is less than n. So what happens then is that some of the poles, m of the poles, will be converging to the zeros. All right, so the root locus, the closed loop poles on the root locus will be converging to the zeros, okay? So m branches, because we have m zeros, of the root locus converge to open loop zeros. Okay, so those are simple principles. So that means at k equal to 0, I start at the open loop poles. As k goes to infinity, I converge to the open loop zeros, right? But what if m is less than n? What happens to the rest? We have n closed loop poles, right? Let's say you have 2 poles and no zeros, right? Then there's no 0 to converge to. What happens? Think about this example here. You have 2 open loop poles. They met. They have no zeros to go to. If they could find a 0 to go to, they would go there, right? But you have 2 poles, no zeros. So 2 branches will go to infinity. So that's the rule. As k goes to infinity, if you can't find a 0 to go to, you're going to go to infinity. Question is, how do you go to infinity? And there are some rules that I'm not going to belabor about how to do that. Let me just show you my notes, which is everything, of course. So this is what happens when k goes to infinity. So you basically have asymptotes that you will follow to go to infinity. And how many asymptotes you have depends on n minus m, right? Because we have n poles that are looking for a place to go. There are m small m destinations. Those are the zeros that you can go to if they are there. But there's an excess, n minus m. Those have to go to infinity following some asymptotes, right? So therefore, you're going to have n minus m asymptotes going to infinity, and the poles will follow those asymptotes and blow up. If n minus m is just 1, perhaps we have one pole and no zeros, right? That was our example 1. Then the asymptote points in this negative real axis direction. Okay? If we have n minus m equal to 2, that means 2 poles more than zeros. Then, as we've seen in our example, there are two asymptotes. One is going vertically up, the other is going vertically down. Okay? So their angles are 90 degrees. So there's a general formula to determine what the angles of those asymptotes are, and that's the second box expression here. So if n minus m is 1, that tells you one thing. I equal to 1, right? N minus m is 1. So that tells you 180 degrees the angle of the asymptote. If n minus m is 2, like in our example 2, then this will give you positive 90 degrees and negative 90 degrees as the angles of the asymptotes. If that's 3, can you tell me what happens then? Let's say n minus m is equal to 3. What are the angles of the asymptotes? Yeah, 180 I minus 1 times 360 by 3, right? And minus m goes in the denominator. So that's 60 plus I minus 1, 120. So for I equal to 1, we have an asymptote that makes 60 degrees. For I equal to 2, we add 120 to it, so that becomes 180 degrees. Will we say that again? Yes, absolutely, and that's why we're not going to let k go to infinity. Large gains have these problems. That's why we had one example so far where n minus m was 1, and only one asymptote going to negative infinity. Therefore, you had no drawback associated with large gain. You just went farther away. But now, in this plot, when you have 3 poles in excess of zeros, you have asymptotes at 60 degrees, 180 degrees, and 120 more. That would be negative 60 degrees, right? So what that means is that the poles will follow these asymptotes and go to infinity. The one going this way to negative infinity is no problem. It's going in the right direction, negative, right? But these guys will eventually cross the imaginary axis, and they will create instability. All right? So that's why high gain in general is not a good idea, but for small n minus m, it may be okay. All right? So what if n minus m was 4? What would be the angles here? (180 by 4 is 45. 45 degrees. Add 90, you get negative 45. So now you have 4 asymptotes that are like this, right? So that's how it goes. Okay, so that's another principle. So root locus starts at open loop poles. It converges, some of the branches converges to zeros. If there aren't enough zeros to go to, then you go to infinity following these asymptotes. It's very simple. Another useful thing to know is which parts of the real line are actually on the root locus. Okay? And very simple rule for this, derived from this principle I was telling you about. So you want the phase of h of s to be 180 degrees, right? So the rule says to determine if a segment of the real line is on the root locus, you count the poles and zeros to your right. Okay? So in this example here, if you're wondering if this point is on the root locus, you ask yourself, is there anything on my right? Nothing. Okay, so you're not on the root locus. the moment you cross a pole, you have an odd number of poles on your right, right? 1 pole. And that makes you lie on the root locus. So the rule is that if you have an odd number of poles and zeros to your right, then you're on the root locus. Okay? So anything here has 1 pole to its right, therefore this is all on the root locus, but this point is not, right? In this example, we have 2 poles. This point is not on the root locus because there is no pole. At this point, you have 1 pole to your right, and that continues until you reach this point, right? Once you pass this, you have 2 poles on your right. Even number makes you 0, or even numbers will make you not be on the root locus, on the real line. Okay? The principle is very simple. Remember, we wanted for a point S0 to be on the root locus, we want this to be 180 degrees, right? So if I pick a point S0 here, then I'm looking at to determine the phase of h of s, I'm looking at the phase of my distance, so S0 minus beta k, which is the 0, and S0 minus alpha k, which is the pole. If those are all to my left, these are just vectors that are pointing in this direction, right? But if you have a pole or 0 on your right, then you're talking about a vector in this direction. So for each pole or 0 on your right, you add 180 degrees to your phase. If you have an odd number of those, then it's an odd number times 180, which is 180, which means you are on the root locus. If you have an even number, then it's an even number times 180, so it's 0, you are not on the root locus. So it comes from that basic principle we discussed. A very simple rule, and immediately tells you which parts of the root locus of the real axis are on the root locus. So going back to this example, remember the segment between these 2 open loop poles was on the root locus. Just a second. And therefore, it is on, it's part of it. If you are to the right or to the left, then you're looking at an even number of poles, and you're not. Yes? Say it again? We'll see examples of that. But after a short break, 5 minutes. Right? Have you seen these SpaceX Falcon 9 landings? The rockets, and then, so the vision here is that, you don't fly an airplane once and throw it away. Why are we doing that to rockets, right? But how do you bring them back, intact? So that's what SpaceX has been working on for a decade. And if you go to YouTube, there are very cool videos. I have one here for you. That's your break entertainment, if the internet works out. Do you see anything there? At the bottom, you see the view from the rocket. And is the cool part. Look at the top left. Isn't that cool? That's control. It's feedback. It's not too different, essentially, than trying to balance a stick in your hand. Okay? It is very difficult control, by the way. I mean, it's because in this case, you're trying to control an unstable system, a system whose open loop poles are actually in the right half plane. Right? You're trying to bring them back to the left half plane, and not an easy task. And in fact, there are some videos of how they got there. Although I don't want to spend too much time on this, it'd be cool to watch some. Okay. Unfortunately, that's on my phone only. How not to land. Okay, let me search. This is called How Not to Land an Orbital Rocket Booster. So these are all the failures that came before. There you go. There's some tacky music which I'm going to turn off. These are some earlier attempts that weren't so successful. Well, they have fuel, impact plus fuel. Anyway, enough disasters, I guess. Actually, SpaceX was motivated by an earlier NASA program several decades ago, Delta Clipper. It was also supposed to do this vertical landing. But it failed just like these ones. And in fact, in that case, I think one of the legs didn't come out, so it just tipped over. It was a very simple failure. But then I think NASA had no funding to pursue that further, so they kind of revived that idea. Okay? Okay, I'm not going to do any more Elon Musk propaganda here, but all right, so let's go back to root locus. So of course, simple constant gain feedback is not going to work when you're doing these things. You need a lot of interesting control actions. In fact, I heard that they had to add these the grid fins at the tip of the rocket to be able to succeed. So they use that as a stabilization, as an extra control to stabilize as you're landing. They have 4 of those. You can search by SpaceX grid fin, and you'll see the design. They have 4 of those. I imagine they move 4 independently. So that gives you a lot of degrees of freedom in the control. All right, so okay, back to root locus, back to the basics. All right. So what would the root locus for this look like? So we again start with open loop poles and zeros. We sketch them on the imaginary axis. So real, imaginary, and then we sketch the poles first. Where are the poles? -1, -2, and then there's a 0 at 1. Okay. So I know the root locus will start at the poles. So that's one of the principles. Another principle that we just discussed is that that part of the real axis where you have an odd number of pole zeros to your right is on the root locus. So can you tell me which segments of the real axis are going to be on the root locus? So anywhere between this pole and this 0, right? Because then you only have 1 0 on your right, odd number, right? The moment you go to the left of -1, you have an even number of poles and zeros, right? So that's not on the root locus. And then what else besides this segment? Once you go past to the left of -2, again you have an odd number, right? So this segment is also on the root locus, okay? Now, the root locus starts, as you know, at the open loop poles, and the poles start moving. And the rule is, if you have a 0 to go to, go there. If you don't, then you get disappointed and go to infinity. You follow an asymptote. So how many asymptotes in this case? How many zeros? 1. How many poles? N minus m is 1. That means 1 asymptote with angle 180 degrees. This is it. Okay, this guy is going to infinity because it has no 0 to go to, following that asymptote, which is the negative real axis. And this pole is going to this 0. Okay, is it a good idea to increase the gain in this example? No, because you have a right half plane 0, and one of the poles will want to go there. So if you increase your gain too much, then you'll cross the boundary and become unstable. So this is an example of when k large is not desirable. Another example, slightly different. You know, changing the order of poles and zeros actually makes a big difference. So the next example, this was 3, I think, in the notes. This is 4. Now we're going to look at s plus 2 by s times s plus 1. This time there are no poles or zeros on the right half plane, but there is a pole at 0, which is borderline. Okay, what do I do first? Mark the poles and zeros, open loop ones. Pole at 0, pole at -1, and the 0 at -2, right? Quick, what's on the root locus if you look at the real axis alone? Anything between these two poles, right? Because you have one pole to your right, odd number. What about between -1 and -2? Yes or no? No, because 2 poles, even number. To the left of -2, 3 odd number, so that's part of it. Okay, so these two poles clearly started moving towards each other, right? And then, again, remember the rule, as k goes to infinity, one pole will converge to the 0 at -2, and one will go to negative infinity. So the asymptotic behavior is not different from this example, because we have, again, 1, 0, and 2 poles. Therefore, we have one asymptote going to negative infinity in the negative real axis direction. So then how is that going to work out? So these poles move towards each other, and how is it going to be possible that one goes to the 0, the other goes to infinity? Can you predict what's going to happen in this picture? So you know the end of the movie, right? So one pole goes to 0 happily. The other is very unhappy, goes to infinity, right? So, but how do we get there from the beginning? The beginning is they started at the open loop pole positions here. Yes? Yeah, they have to somehow break away from the real axis somewhere, right? They move towards each other. Remember what happened when we only had two poles and not that 0? They met in the middle, and they broke away going, to infinity vertically. This time it's not going to be vertical, because in that example we have two poles and no zeros, right? So we have 1, 0 now that we need to go to. So, but the breakaway part is going to happen. It's not going to happen in the middle, I can tell you that much, because we don't have the symmetry we had in this example. The 0 broke the symmetry. But nevertheless, something like this will happen. So they'll meet somewhere, not necessarily the middle, and break away into complex poles. And now what happens? Again, the end of the story is one is going to go to -2, and the other is going to go to negative infinity. And remember, everything on this line segment is part of the root locus. So those two poles that are now complex, right? They are going to make a detour, come back and meet again on the negative real axis. Okay? So it's going to look like this. Okay, the drawing is not perfect, but they meet again as I increase k somewhere here. And what happens then? One of them goes in this direction to meet the 0, and the other goes in this direction to negative infinity. I guess it wasn't a great drawing, but it looked like this in the end. Like that, okay? So once again, as I increase the gain k, these two guys start moving towards each other. They break away here. They make a detour, meet here again. So at that point, again, I have two repeated negative poles. Afterwards, one goes here, the other goes to negative infinity. Okay? That's the root locus for this example. And in fact, turns out, I'm not going to prove that or anything, but this is a perfect circle with the 0 at the center. So this portion is a perfect circle when you have two poles and 1, 0. Okay? And the points where you break in and out, this point and this point, are determined. Again, this is a property that I'm neither going to prove nor expect you to prove. These are determined from solving for the roots of dh of s by ds equal to 0. Those roots of the derivative that are on the real axis, they become the breakaway and break-in points. So if you apply it to this example, to this transfer function, this rule, if you look at dh of s ds equal to 0, you could do this as a simple example. You get a polynomial equation and you get two roots, and the roots are -2 plus minus square root of 2. -2 is really this point, it's the 0, right? And plus square root of 2 puts you here, minus square root of 2 puts you here. So therefore, this is a circle with radius equal to square root of 2, right? Not very important that it happens to be a circle, but it is, and it's cool. So why is this true? Why is this a break-in, breakaway point? Yeah. Okay, I can assign a homework problem on that if you're interested. Okay. Agreed, we're happy. All right. Any questions on this? Yes. Well, I mean, from the few rules we discussed, right, we know that they have to either go to infinity or to a 0, right? We also know that this segment here is part of the root locus. So somehow they have to come back there, right? And, you know, so that one can go here and the other can go there. There are a zillion other rules for sketching the root locus. If you follow them, you would make a nice sketch. Very detailed one, but we don't need that because we're just trying to pick on a few simple principles that give us intuition about how feedback changes the closed loop poles. I don't care if you make a very accurate root locus plot or not, because you can use your computer to do that for you. Yes? I mean, doesn't matter, because for every k, I mean, every point there on the orange curve is a k, right, a gain. So you look for poles there, and you know, you look at the roots of that, and you get a bunch of solutions that are on that curve. So it doesn't matter who was who, right? I mean, you have a new set of poles. It's not like one of them maintained its flag and went in that direction. So you have two poles, one happens to be here, the other there. Other questions? So, okay, for those of you 16B veterans, yesterday was Veterans Day, right? So you are veterans. So you did something, I assume, on how to place by feedback the eigenvalues of a system, right? You didn't call them poles then, you called them eigenvalues, but we've seen they are the same things really, okay? So how different is this discussion than that? Sounds similar, right? There you want to place your poles at desired locations, and similarly here. But there you were doing something that we called state feedback. So you had a differential equation model with your state equation. Let me call it Z, because we don't want to confuse with our notation in this course. A Z of t plus b times x of t, right? And then you said, okay, I'm going to choose my control x of t to be a matrix K multiplying the state Z of t. Okay, what does that lead to? It gives me a closed loop system that looks like A plus BK times Z of t. And then you said, well, how do I choose K? Turns out if the pair A and B had the so-called controllability property, then you could always choose a K that placed the poles of this matrix arbitrarily, wherever you wanted them to be. Do you remember that? At least roughly you should remember that, okay? So what's different here? Why am I now restricted to a menu to choose from this locus? Only that on that locus I can get a closed loop pole. Here everything worked, right? I could put my poles wherever I wanted. Yeah, I mean, you could still do that. I mean, that's not the key issue, okay? Right? Yes? Yeah, but look at the, yes, I mean, you're all to some extent right, but look at the structure of the control. What does that tell you? Input is K times Z of t. What is K here? Gain or gains? Z is a vector, right? Z is a vector. So you measure every state variable there. You multiply each one with a gain, add them up, and that's why we call it state feedback. You're measuring every state and composing them to create a feedback. Whereas what we're doing here is we're doing what we call output feedback. We only have y of t there, right? And feed that back. K is a gain, not plural. Okay? So the equivalent of that in the 16b setup would have been, you're also specified an output. Let's say c times z of t, right? And your controller is now x of t. Let me use a little k to indicate that it's just one number, one parameter, not a vector, times y of t, okay? So, in fact, we use negative feedback, right? So then what we get is this becomes negative k times c times z of t. So our closed-loop system is now a minus b k times bc z of t. Okay, that's the difference, okay? So here k is a whole row vector, whereas here it's just not one number. So you can't expect the whole world from changing one number there, right? I mean, it's just one gain, right? So that's why we're now restricted to only certain parts, certain loci on the complex plane where we can choose our poles from. So that, of course, points to a limitation of output feedback or constant gain feedback. So we essentially come close to state feedback by using controllers that are not just constant gains but have their own poles and zeros and things like that. Okay? So I'm not going to completely connect the two, but I want you to see that in both classes you are trying to place your closed loop poles. Now your hands are tied a little bit because we are doing only output feedback. Any questions? If you're landing a rocket vertically, you're not going to get away with output feedback. Okay? You'll need state feedback. In fact, most likely you'll need more than one input, right? I mean, the simplest scenario is you have just this horizontal motion to balance something. Maybe theoretically on paper you can stabilize it and run simulations where it lands, but in practice there are too many things going on. So for a more robust stabilization, you would need many control inputs. That's why they added those fins at the tip to give them more control authority. All right, back to root locus. You know, I'm obsessed with root locus plots because they're so cool. You know, roots of the polynomial, how do they change when you change a parameter that goes into the coefficients of the polynomial? Isn't that cool? You know, I mean, you still have n roots, but it shows you how they move as you change the coefficients. So they're actually useful beyond just, you know, analyzing step responses and things like that. So let's look at my final example here. Okay, this is the last of the examples, I believe. All right, so now we have, it's like the example above, which was s plus to that circle example. Same thing, s plus to s plus 1. There's only one difference. We added one more pole at negative a, and we're assuming a is bigger than 2, so that means there's now an extra pole here. That is going to change things fundamentally, all right? Because now you have 3 poles and 1 0, right? So the new picture is like this. Those poles that were there before remain. The 0 is still here, but then I have a farther away pole, right? So can you help me with a discussion of what would change really in this case? So which segments of the real axis are on the root locus? Okay. Now, what is one scenario that could happen? So we have 3 poles, 1 0. We will have 2 asymptotes, plus minus 90 degrees, right? When there are 2 asymptotes, they go plus and minus 90 degrees. And one pole will end up at the 0, right? So what are some of the things that can happen? Yes? Okay. So that's the idea. There'll be a breakaway. It's not going to be exactly breakaway in the middle and go straight, because that was the scenario for two poles and nothing else. Here I still have the 0, and in fact, if this pole is far away to the left, the two root locus plots should look more or less the same. I mean, eventually for large gains they'll look different, but it will actually look as if it's breaking into a circle and going to come back, right? But what happens is that eventually they go to infinity, okay? And this guy goes to that 0, okay? So that was one thing in the formulas that I showed you. We not only talked about the angles of the asymptotes, but we also talked about the center of the asymptotes. Where are those asymptotes springing from, right? And that was this formula that I didn't dwell on, this one. You basically add the poles, subtract the sum of the zeros, divide by n minus m. That tells you where the asymptotes are rooted in. In this example, that would be a point. What's going on here? It's basically some point here. It's not necessarily the point of the 0, but this is the center of the asymptotes. This is number of poles, sum of poles, minus sum of zeros by 2, whatever that number is. And clearly, as this pole at negative a becomes more negative, that moves also to the left. Okay? So that kind of looks like if I was moving this pole on the left further away, that would look closer and closer to being a complete circle, right? Because that center of the asymptotes would be moving to the left, right? So this segment here will look closer to a circle initially before turning away. In fact, if you keep increasing a, that means moving this guy here. Yeah, it's very hard to write on this. If I keep moving this further to the left, something really funny happens. If I don't expect you to do all of these, numerically or anything like that. I mean, MATLAB could do it for you. But when I choose a really large, the shape of the root locus changes from what I have here to, which is this. This is what we discussed, right? To this one. Isn't that funny? So what happened now is that this pole at negative a was so far away that the root locus was pretty much like the root locus of two poles and 1, 0, like with that circle, right? So those two poles met, they broke away, and they broke in again, right? And one is going to that 0. The other thinks it's going to negative infinity, but no, there's another pole that's coming from that direction. Those two collide somewhere in the middle. They break away again and go plus minus 90 degrees up. Okay? So that's why I kind of find root locus plots very intriguing. There's a lot of intrigue in these stories. Poles, break away, they come back together. They go to zeros happily. You can make all kinds of stories about them. So, okay, like I said, you will not get a maybe homework, but never an exam problem where I say, here's a very complex transfer function, 10 poles, 20 zeros, whatever, and draw the root locus very precisely. There's no point in that. Okay, maybe simple ones, but not complex ones. And so why am I even doing this? Well, just these very few rules that don't allow you to make a very accurate sketch, but just to give you the general idea of what happens, who goes where type of thing. Gives you a lot of insight and intuition. For example, the question of whether or not I should crank up the gain or I should not is answered easily by one of the principles of root locus, the fact that poles go to either zeros or the infinity following asymptotes, right? So if your n minus m, if you have 2 poles, no zeros, or 3 poles, 1, 0, if n minus m is 2, on the surface, we have nothing to worry about, right? Because they'll break away, they'll go to infinity vertically. But still, even though stability is preserved, you should still worry, because what happens as you increase the gain? The damping is worse and worse, right? You have imaginary parts that are really large, and those will give you huge overshoots in your step response. You don't want that, right? So already when n minus m is equal to 2, high gain is not free. It has drawbacks. If n minus m is equal to 3, then high gain gives you actual instability, because now the asymptotes have those plus minus 60 degrees, so you cross into the right half plane and become unstable. Okay? Too aggressive a gain can destabilize your system. Make sense? All right, n minus m4, same story. You'll go to the right half plane even sooner because the asymptotes are 45 degrees. So basically the story is, if n minus m, that quantity is called the relative degree of the transfer function, because it's the degree of the polynomial minus the degree of the denominator minus degree of the numerator. If that relative degree is 3 or more, you get instability with high gain. Okay? And regardless of that, if you have any right half plane zeros, high gain instability again gives you instability, because one of the branches of the root locus will go to that 0. And if the 0 is on the unstable side, then you'll become unstable. All right? So now you see that high gain can create instability. So it's not necessarily a desirable thing. Any questions? You sure? Okay. So let's now talk about how we actually bring that to control design. I mean, we sort of alluded to that, but to make it a little more explicit. So let's go back to our example. Again, we have this car, and this is the example where we are trying to control the position at a set value. Okay, so the blue one is the root locus. We discussed that before. We had two open loop poles. They met in the middle, went to infinity with plus minus 90 degrees, right? The blue is the root locus. Now, how do I select? Now I know that's my menu. I can select close. If I'm doing constant feedback gain control, those are my options. I can put my closed loop poles only on those on the root locus. But where should I select them? What gain k should I select? In other words, which points should I select on the root locus? That depends on what kind of step response, for example, you want to have, right? Because the closed loop poles are going to tell you the type of the step response. If you want smooth convergence with no overshoot, then you want real poles, right? Then you should select your gains so that the closed loop poles happen before you break away, right? If you can tolerate a little bit of overshoot, then you can get faster response. Of the two parameters, remember we had C, that was the damping ratio, that was cosine of theta, where theta was this angle, right? For a second order system, correct? And what was omega n? It's the distance to 0, right? For a second order system with complex conjugate poles, those are the two parameters we use. C is the damping ratio, or zeta, I guess, and omega n is the natural frequency, distance to the origin. So what roles did they play? How many of you remember? We looked at those step response plots, frequency responses. So in terms of step response, what does omega n change? The speed of the response, right? It just stretches it out or compresses it. How do I compress it? How do I get a faster response? Larger omega n. Put your poles farther away, right? What did the damping ratio change? Resonance in the frequency response, but let's now talk about the step response. The amount of overshoot, right? So if zeta was 1, that was the case where the two poles are on the real axis, then you don't have any overshoot. The moment theta is bigger than 0, you'll get overshoots. And as theta becomes bigger, that is, theta becomes smaller, closer to 0, then you're going to get huge overshoots. Okay? So now when you're designing your system, you may have objectives like how fast I want to respond. Ideally, you want to be fast. You want a large omega n, right? Okay? Large omega n is good, fast response. You also want good enough damping so you don't overshoot too much. Right? So low damping, in this scenario, like low C close to 0, I'm not going to write it, but C close to 0 and omega n large are desirable things. So let's look at this menu. I can make omega n really, really large if I put my closed loop poles like here and here, right? Because then the distance to the origin is very far. Yes? Is that a good thing? Yeah, that will give you a lot of oscillation because the damping is very low then, right? So, then I may worry about damping and say, okay, well, I don't even want any overshoot. I'm going to put my poles here, both at the real axis. But then your distance to the origin is not maybe great, So that's how basically you make the design choices. You worry about how far you're off from the imaginary axis. That's the omega n. And what your damping is, that's the C, right? If my only goal was to get a damping ratio of 0.7, that gives me an overshoot that's like 5%. That's usually quite reasonable. Then you can superimpose the lines where the angle is 45 degrees, right? Then these are the points you want for your closed loop pole. That will give you 0.7 damping ratio, okay? And I don't know about Python. I think Python has some toolbox somebody developed, but MATLAB is a very professional one where you actually, it's called RL tool. You give the open loop transfer function. It gives you the root locus. It also allows you to move the cursor on the root locus, and it shows you, when I click here, it shows me what the gain is, what gain K is to put the closed loop poles there. Okay? All right. But like I said, typically we would both want the damping ratio and a lower bound on omega n. That tells us how fast we want to go, right? So lower bound on omega n means that your distance, the distance of the closed loop poles to the origin, should be bigger than some given radius. So it would be the exterior of a circle like this that has radius omega n. Okay? And then if you want your damping to be less than something, that means the angle here should be smaller than something. So to meet both objectives, you'd be in a region that looks like this here, right? This is the region of points where omega n is bigger than a number and zeta is bigger than a number. That is, theta is smaller than an angle, right? So then you may ask, can I select a gain so that my root locus passes through this region? Because that region is a set of acceptable closed loop poles that will give me the desired response. So if this is your root locus, what's your answer? I gave you an omega n. That's this value, okay? And I gave you a zeta below which I won't be happy. That's too much overshoot. I can't tolerate that, right? So the acceptable location is the shaded region. And this is the root locus I have. What should I do? Well, is there anything to do? I mean, the root locus doesn't go through that region, period. The train doesn't go there, right? You can't achieve your goal, those specifications, with this given control architecture, which is too simple. Constant gain control. You look at the error, multiply it by a constant, feed it to the system. That simple scheme is just too simple. It's not going to get you to your objectives. All right? So what should we do? Is that the end of the world? Well, remember at the beginning we had our Oh yeah, you can tweak your specifications, sure, but you don't want to do that, right? I really want closed loop poles in the shaded region. And this just tells me, this picture tells me here, constant gain control won't do it, period. Okay? But why constant gain control? I mean, at the beginning, we had this general scenario, right? The controller itself was HC of S. It could have its own poles and zeros. It didn't have to be a constant gain. Does that make sense? So why don't we have the controller include a pole and zero itself? Okay, so does anything come to mind now? So let's change the architecture. Going back to this example. Let's now say our control is not a constant gain. It's a constant gain times a zero and the pole. I had it here. Okay. Well, anyway, all right. So can you propose? So what does this change if I choose this control architecture? It's a more complicated controller. It has a zero and a pole. It's basically some kind of filter itself, right? But essentially what it changes is, what we're going to look at to determine the closed loop poles is we're going to look at the roots of this, right? S minus beta, S minus alpha times the plant transfer function of S. So that means we can apply the root locus rules to the combination of the plant with the addition of this pole and zero, right? So I'm no longer tied to just picking a gain. I can pick the gain, yes, but in addition, I can put a zero and a pole there that will be coming from my controller. So any ideas where you might want to put a zero and a pole to make the new root locus pass through the desired region? Well, I mean, shaded region is where you want to go, but you're still, when you select alpha and beta, you still get a new root locus. It will just be a little different than the blue one, right? So you want to put a pole and zero so that the new root locus goes through the shaded region. Okay? Do you have any ideas how you might select the zero, for example? Why don't I put a zero right here on top of this pole? So that means the controller zero cancels the plant's pole. So essentially, it's gone, right? But I'm also going to add a pole. You don't want to have a controller that is just single zero. Why? Because then you have only S plus something in the numerator. That means you're taking the derivative of a signal, right? That will create a lot of noise because the signal whose derivative you're taking will likely come from the sensor, noisy measurements. You don't want that. You usually want to pair it with a pole to balance it, right? So keeping in mind that we also need to add a pole, where would I add a pole? Yeah, if I put it far away, really, this pole zero pair essentially did the following. It removed that pole that was there in the first place, moved it far to the left at the point of your choice. What does the new root locus look like? That pole is gone. So the new root locus is like this. But then in the middle, this is a horrible plot, but yeah, they meet in the middle and go. And then now you can make it pass through the region you want, right? Does that make sense? So the key feature of this is that you have the controller added a zero closer to the origin, and the pole farther away. Okay, that's the key feature of this controller. You didn't really have to cancel that pole. I'm going to cancel my cancel. Instead, I could have, you can always do that. If you know that pole, you can cancel it. But you can also add a zero somewhere and another pole. And what's the effect of that, remember? Two poles. This was one of our examples. Two poles, one zero, and another pole. These start here. They move in. And then they get repelled by this pole. and they go like this. So even if you don't cancel that open loop pole with your 0, you can still pull the root locus inside or into the left half plane. Okay? So the key element of this controller is to use the 0. 0 has the effect of attracting the root locus, pulling it closer to itself, right? That's what we saw when we go from one example to another here. Yeah, the example where we had 2 open loop poles, they just go into infinity, right? And then you add a 0 to the left of those guys, and all of a sudden, that 0 attracts the root locus. Instead of going to infinity, now the root locus breaks in to reach that 0, right? So 0, since it's a final target for the poles, will have the effect of attracting it. Adding a pole, on the other hand, will kind of repel it. That's why here, these guys are, these 2 branches are folding back and running away. Once they see the pole, they run away, right? Okay, so that's the relative effect of 0 and pole. 0 attracts, pole repels. So what we really want with our controller is the effect of the 0, because we want to use the 0 to lure the root locus into the left half plane, right? And that's what this 0 here does, this one here. Okay? The pole is only there to be a pole and to not leave the 0 alone, right? So you want to have a 0 and a pole in your controller. So the essential structure of the controller is a 0 that is dominant, that is closer to the origin, and the pole farther away. So give me an example of a control transfer function that does that. Dominant 0 and less dominant pole. K is still something we're going to design based on root locus, but we get to add poles and zeros. So give me a pole and 0 pair where the 0 is closer. -1 and -10, does that work? If this was -1, this was -10, would that be okay? All right, so what is the transfer function then? S plus 10. Okay, controllers of this form that are not constant gain controllers, but they come with a pole 0 pair where the 0 is the dominant one. 0 is closer to the origin. They are called lead controllers. And they are very useful. Essentially, they try to mimic what a 0 by itself would do. Attract the root locus into the left half plane, make the closed loop poles more damped, more faster, converge faster, right? Why is this called a lead controller? It's a historical term. It has to do with what kind of filter this is. I mean, ignore K for now, right? So, this is like the body plots we saw, right? There you go. S plus 1 by S plus 10. That's the lead controller. Here's how you make a body plot, right? What kind of filter would you call this if you had to call it a filter? Started at -dB, went up. It's high pass-ish, right? So higher frequencies have an easier time going through. They go through with 0 dB, otherwise lower frequencies are suppressed, right? But if you look at the phase, remember for every 0 you have the phase going to 90 degrees. For every pole, it's going to -90 degrees. When you make body plots, it's an addition of the 2. If the 0 comes first, then you start going up, and then pole comes into play and brings you back to 0, right? Because of the relative ordering of 0 and pole, in the lead filter, you'll first get the phase increase, and then the pole kicks in and brings it back because the pole is farther away, right? So that makes the phase look like the orange plot here. It's a bump. That's why this is called a lead filter, because people say this controller has a phase lead. So it has a positive phase. Okay? So it's a reactive controller. It's sort of jumping the gun. So it's trying to bring the poles into the left half plane. Okay? That's the genesis of the lead controller. Okay, should I set you free here? All right, so what is today? Tuesday? Okay, we'll talk more on Thursday. Maybe we'll do a quick summary too.